So I'm going to be talking about some work that I've been doing looking for and fixing undefined behavior in a whole lot of crates across the Rust ecosystem. And to start off, I have two links. The top one is a repo that contains a lot of the analysis and automation that this is based on, and the bottom one is a website that contains a whole bunch of output logs from a tool called Miri. You can browse it at your leisure, and if you find some code that is precious to you, maybe that you've written on there, feel free to hit me up. So, but by means of introduction, undefined behavior, or UB, I think is very much the essence of unsafe programming. Uh, we want to have a fast optimizing compiler, and optimizations want to make assumptions about your code. So there are on all unsafe APIs, or almost all, preconditions that you must meet, and if you don't meet them, you execute what's called undefined behavior. The compiler may assume that you meet the preconditions and optimize based on that, and then what you get out if you don't meet the preconditions can be nonsense. But I think that actually every programmer should care about this. Maybe even if they don't interact with it, they should care at some level, because basically all programs are built on unsafe foundations. Those are through the standard library, or they're through common ecosystem crates like Tokyo. And undefined behavior is very often a time bomb, which is why all of this that I'm talking about is looking for undefined behavior proactively. Undefined behavior is typically exploited by optimizations, but our compilers are always getting better. Even over the relatively short lifetime of Rust, the compiler, the backend that the Rust compiler uses has gotten significantly better, and it has been able to turn some patterns from fine, like not weaponized by the compiler, into much more dangerous things. So it would be very interesting to look for this sort of thing proactively. I sort of worry whenever I talk about this that people get the impression that from me talking about bugs that I'm finding in other people's code, that I'm like smarter or something, or that I'm, that I really understand what I'm talking about. And I don't, which is why I have this quote here from C++ consultant and speaker Nikolai Yasutis. He says, "I'm not that smart. That's my primary benefit." And I really feel this. The approach that I take to finding bugs in code is not one of great understanding or something. I lean very, very heavily on tools. So the tools that I'm using here are Miri. Miri is a Rust interpreter, which is designed to execute Rust code and check it for every form of undefined behavior that we can come up with. Everything that the Rust compiler or LLVM may rely upon. Miri is very slow. It is not a serious way to execute your code. It's a good way to find bugs. Miri is slower than if you rewrote your Rust code into Python. The standard library also has debug assertions in it. So whenever there's an unsafe API in the standard library, there is actually a debug assertion in almost every case. There's a debug assertion that will check it in debug mode, but you need to recompile the standard library to get access to these. So you need a nightly compiler at the moment. The other tool that I'm using is AddressSanitizer. AddressSanitizer is technology from the C and C++ worlds, which we can use because we share a compiler backend, and we also share a lot of the most basic sort of pointer allocation undefined behaviors with them. So it works pretty well for Rust. And again, in all of this, I'm just running people's tests. This is strengths and this is weaknesses, and I'll touch on them later. So I did actually manage to run Miri on every single crate on crates.io as of a couple days ago. And almost 5% of those crates report some form of UB under Miri, which is interesting. I'm never sure if that number is high or low compared to what people are expecting. The good news is that the biggest category of these is some sort of pointer aliasing problem. So one of the things that Miri does is it implements a prototype aliasing model. There is no accepted aliasing model for Rust. So there's some rule for how references and pointers need to interact, but the rules aren't fixed yet. And we actually know that the prototype rules that are implemented catch certain patterns that we want to be well-defined and call them undefined behavior. So this 1,600 is high, but we sort of know that it's supposed to be high, and it's encouraging now that we actually have some data to go on from this of what people are actually doing that's rejected by the prototype rules. The next biggest category is misuse of uninitialized memory. Rust has significantly stricter rules about what you can do with uninitialized memory than C and C++ do. And for a while, we didn't do a very good job of teaching people about them, and it shows. The next biggest category is a very sad story. BindGen emits tests that do a subtle null pointer problem. And that's really unfortunate. It took a long time for this issue to get patched. And so people ran the bindings generator. They then checked in the code that the bindings generator emits into version control, and they ship it. And so the bug here is in the unit tests that it emits. So it doesn't actually affect anyone. It just trips me up. So this is a significant weakness of just relying on people's tests. And the next biggest category, right, we take a huge drop, right? So these from these first three categories are very big. The next big category is misaligned pointer access, and this is one that I'm doing some other work to try to help people out with. It's a little bit subtle, and it seems to me anecdotally that this is mostly done by people with less experience in Rust. But eventually, right, far down the list, sort of as we get to smaller and smaller categories, we get to some more familiar bugs. Use after free, data race, but also what's interesting about Miri is that Miri doesn't have canned checks for just a few forms of undefined behavior. It checks for so many things. So I've seen all kinds of issues. My favorite at the moment is one crate has a thread that tries to join itself. I haven't dug into that. I'm not even really sure how you code that up, but Miri does some creative things to try to massage code that's running through it into sort of expressing issues. So standard library debug assertions, right? These are relatively simple. They're not nearly as complicated as Miri, so you can use them on a lot more code bases, right? And I've run this on much fewer crates, and of course they check for far fewer undefined behaviors, but what they find are a lot more sort of exciting if you're looking for serious bugs. So when you do a get unchecked onto a slice, the index needs to be valid for the slice, not just the allocation that the slice references. And it seems like some authors didn't know. This has only been documented very clearly in the standard library for 3 years, but there has been some code written since it has been documented. So I think people just sort of misunderstand this API. So that's sort of interesting. And then again, misaligned pointers, right? People also, I think, generally know that references can't be null because of the bit packing that goes into making an option of a reference the same size as a reference. But very often when people are working with FFI, they'll get a pointer and a length back from some C or C++ API, and they'll think, oh, I should make a slice out of that, and forget that they need to check whether or not the pointer is null, because it's not uncommon to get a null pointer and a 0 length back, because that would be fine in C and C++. Not so fine in Rust. The other one, this is classic time bomb UB, is copy non-overlapping called with overlapping ranges. It says it right in the name. I'm sure if people knew what they were doing, they'd be like, oh, that's so silly. I knew I'm not supposed to do that. But it's very easy to write this, and the naive code generation from a compiler that isn't specifically optimizing based on this will be to emit exactly what the programmer wanted. AddressSanitizer. AddressSanitizer mostly finds the most exciting kinds of undefined behavior. So buffer overflows, use after free, right? So what's interesting is I found quite a few buffer overflows, but they're almost all from people trying to write SIMD code by hand. So that's sort of interesting. This is, I think, one of those examples where we really want this to be in a library so that people don't have to think so much about the low-level details. The other thing that I found, and this was amusing the first time that I found it and almost depressing the third time that I found it, null terminator confusion. C and C++ have been trying to get away from those for good reason, and it's really unfortunate that in interacting with C and C++ over FFI sometimes, and Rust you need to juggle null terminators, and people get it wrong sometimes. And these insta-dangling pointers are a pattern that we have some lints for in the compiler, but basically people will create a temporary allocation, and then they'll grab a pointer to it, and then they'll use the pointer after the temporary allocation. What's interesting is that I found 3 of these, but they're almost exclusively written in tests, which may or may not say something about how rigorous people are when they're writing unit tests versus the normal production code. So in terms of fixing UB, right, so this title was about finding and fixing. I've sent PRs to about 50 crates so far, and I've been impressed by how quickly a lot of maintainers will take UB fixing patches. I've seen authors who've written code 3, 4, 5 years ago. It's a simple little data structure. They upload it to crates.io. They haven't thought about it since. And then I just, come along and send them a PR like, I found a use after free. Here's a fix. And they'll take it within days, which is, I think says a lot about the kind of people that are in the Rust community. The other thing that's interesting from fixing this, crates rarely contain just one bug. Very often, I'll go into a library where my tools have reported some issue, and I will see one instance of the bug. I'll fix it, run the tool again, and I'll see another instance of the same bug. And then finally, sending PRs is way more work than finding problems. I feel like this is sort of obvious in hindsight, but I didn't anticipate how draining it can be to write up a bunch of these PRs. Whereas doing, the data analysis and just plowing away on that is a little bit more energizing. So advice, right? I feel like I should give people a little bit of advice at the end. Rust-specific UB very much dominates the field. It seems like Rust just generally has done a really good job of squashing the UBs that C and C++ are known for, but we have some of our own, and we're still struggling to teach people about them very rigorously. So I have suggestions, right? Run the tools. So this is how you would run them on a Linuxy system, and I hope that you do. Build this into a SaaS. Yeah, that's a yeah. So the tricky thing with doing anything like SaaS is that the runtime is actually somewhat significant. So docs.rs tries to do this, and docs.rs is just trying to compile documentation, and docs.rs gets kind of bogged down with this long queue of people that publish crates very often. I run new crates sort of at my leisure, and I only run the latest versions. There are crates where I try to sort of run things generally as they're published, but if you publish too often, I'll just miss versions. So that's interesting, but there's a little bit of a resource problem there. How long does it take to run? So I kind of bought a Threadripper just to do stuff like this, and it still takes like a week to run Miri on all the crates. But part of the reason that Miri runs at all reasonably fast is because it just dies on so many crates because it just doesn't support things that they're trying to do. So I haven't gotten any farther than about the first 10,000 crates with AddressSanitizer because it just takes so much longer. Issues caused when programmers caused by 32-bit when programs assume 64-bit. This is a very fun thing that Miri can do that I have not tried to get it to do. Miri supports things like big endian and 32-bit, and also some other interesting architectures that it can model. I haven't gone quite that far yet. Stats on how many crates could successfully be run under Miri. Yes. I believe somewhere around 70% of crates will execute without an error, though that is, I think, strongly biased by the large number of relatively little downloaded crates that are rather simple. They're data structure things, they're typo squatting or normal squatting of some sort. You can actually see that the distribution of runtimes changes significantly from the most downloaded crates, which tend to be very, very big and heavily tested towards the sort of tail. Yeah, so Clippy rules to detect UB, there are some, and those should definitely be improved. Does the borrow checker still work at the Mir level? Yeah, so this is also a really fun question. So the current borrow checker runs actually on Mir. So the output that Miri is executing is already borrow checked. However, there is this open question on Miri about if we turn off the borrow checker and still emit Mir, what kinds of code is accepted by the aliasing model that Miri implements and rejected by the borrow checker. Uh, we think the space there is relatively small, especially as people in terms of how people write Rust code, but it could be interesting. Anything you've learned about writing Rust from running all these tools? Run the tools is what I've learned from writing Rust. Um, I've learned especially that even after all of this, I don't know the rules nearly as well as the tools know the rules. There are times when I'm trying to patch people's code, I'm like, oh yeah, surely this is the transformation that will fix this, and it doesn't fix it. Or I'll be looking over some other code that someone's written. I'll be like, wow, that really looks invalid. But the tool is accepting it, and I swear this, unit test hits this code path, and it turns out that I'm wrong and the code's actually valid.